Good afternoon, everyone. I'm Jong, and a PhD student from the Department of Business Administration at Busan National University in Korea. It's a great honor to be here and to have opportunity to represent my research in this session. Today, I'll brief you on my research topic, optimization of uneven margin SVM to solve the class imbalance in bankruptcy prediction. The purpose of this research is to optimize uneven margin SVM to improve the prediction accuracy and class imbalance data by modifying the algorithm of SVM. The order of the presentation is follows. In binary classification model, there can be many lines that classify between the two classes, but the best classification boundary is one that maximizes the margin. SVM shows a robust boundary based on the margin theory, but in class imbalance data set, is SVM still robust? No. Why? Ricardo algorithm as we assumed balanced data between two classes. I want to show the disease boundary movement process in imbalanced situation. I generated some dataset like this by different imbalance ratio. As the imbalance is getting severe, the disease boundary tends to move to the minority class like this. So the area of minority class gradually skewed. This problem reduced the accuracy of minority class. So in third and first graph, you can see that a disease boundary does not work properly. Another problem in imbalanced data is the performance measurement part. Arithmetic mean accuracy is popular measurement, but it might be inappropriate because it is highly dependent on the accuracy of the majority. Geometric mean accuracy can be used as alternative measurement because this is handling both the accuracy of a majority and minority class at the same time. You can calculate the GM, sensitivity, and specificity using this computation matrix. Several variants of SVM. As we know, soft margin SVM has the same margin SVM from the two support vectors. We can call this even margin SVM or EMSVM. Uneven margin SVM or UMSVM has a different margin size because the decision boundary moved towards a minority class. Even margin SVM and uneven margin SVM has the same distance, but the margin of cost sensitive SVM differs to the cost coefficient like this. Here is the computation of method of margin. Let the support vector of minus class be a plus plane like this, wx plus b equal 1. And let the support vector of majority class of minus plane as wx plus b equal minus 1, and the decision boundary is wx plus b equal 0. And the decision distance between these lines can be determined by transforming these equations. Looking at the function of EM-SVM, that is same with the soft margin SVM, like this equation. Equation 1 is the objection function, and equation 2 and 3 are constraints equation. Focus on equation 3. This is minus plane. It is related to the margin from the support vector of majority class. This is the function of UMSVM. The objection function is same with the MSVM, but in equation 3, This is the constraints of majority class part. It has minus tau instead of 1 of EMSVM. It is margin parameter that adjusts margin of two classes. And Ryan-Taylor, it is defined as a ratio of margin of majority and minority. Tau is a value greater 0 and less than 1. If tau is 1, EMSVM is the same with UMSVM. If tau is between 0 and 1, it means UMSVM. Here is the comparison of EMSVM with UMSVM. Minus 1 support vector of the majority class is transformed as minus tau. Because tau is less than 1, the margin of majority can be reduced. So the margin of minority is larger relatively. This figure shows the classification results of two models. Here, observation of majority class are shown as minus, and observations in minority class are shown as plus. The solid line indicates the hyperplane, and the dotted line indicates the support line of the majority class and minority class. In figure A, the margins of two classes look same. And large A is originally one of minority class, but is misclassified into majority class based on the hyperplane of EMSVM. UMSVM sets a new hyperplane green line by moving the hyperplane in the direction of majority class using tau, as shown in figure B. In figure B, large A is correctly classified as minority class. The larger the margin, the higher the accuracy. This is error tolerance ability. It means that margin increases the generation ability of SVM. In UMSVM, the margin of minority class is larger than the margin of majority class, so the sensitivity of minority class can be improved. So my first research question is, in class imbalance problem on SVM, how to readjust the margin of minority to improve sensitivity and geometric mean accuracy. And my second research question is how to optimize UMSVM. It means that how to optimize margin parameter tau in UMSVM. To optimize tau, Ryan-Taylor applied random search technique. They selected tau among random real variables between 0 and 1. They found that optimal tau was somewhat related to the data imbalance ratio, but they could not define the functional relationship between them. Ryan-Taylor tried perceptron algorithm and UMSVM, but perceptron can be applied only to linearly separated data. In this study, I applied threshold method as an optimization algorithm. This method is frequently applied in class imbalance problem. The threshold of the label is generally set to 0, but if the threshold is fixed at 0, the specificity of majority class is overestimated and the sensitivity of minority class is underestimated. For this problem, a threshold moving method set threshold flexible. So I propose OPT at UMSVM, that is optimize the UMSVM. OPT-UMSVM algorithm is finding out tau using threshold moving method. Sensitivity can be closest to the specificity by this method. At this point, GM is maximized and AURC also is maximized. I can summarize the procedure like this. First, fit the model on the training data set, and second, predict probability on test data set. Third, repeat the following for the several threshold points, and finally use adapted threshold when making class prediction on test data. Such that the weight of UMSVM is same with the weight of EMSVM, but bias of UMSVM differ from EMSVM. In UMSVM, by tau, the boundary of EMSVM is moved in parallel. In OPT UMSVM, the movement of decision boundary is set as threshold T, and at this point, tau becomes the optimal margin parameter tau star. At this point, the sensitivity and specificity is almost matched. Based on this point, the equation for the decision boundary of each models are like this equation. For the experiments, I had 500 bankruptcy and 7,500 non-bankruptcy companies from a Korean commercial bank. I have made 5 sub-data sets by imbalance ratios. I have split them as train set and test set line to 1 to validate. The hyperparameter C and gamma of EMSVM was determined by the grid search method. This table adapted the final input variables as follows. I collected 30 financial ratios based on the prior research and separated these ratios as 7 groups based on the prior research and practice. Finally, I selected 7 financial ratios with the highest AUROC within each ratio groups. This table shows the result of first research question. I applied different tau for each subsamples. To summarize the result, first, the lower tau is the lower specificity as in all subsamples. This means that as tau is lower, the moving distance of the hyperplane of UMSVM increases. The specificity of majority class decreases. Second, the sensitivity is greatly moved as tau is lower, and it means that the effects of UMSVM is larger as the class imbalance is severe. Third, arithmetic accuracy tends to decrease continuously and gently as tau decreases. This is because arithmetic accuracy largely depends on the specificity of majority class and does not respond well to the sensitivity of minority class. And finally, geometric mean accuracy shows inconsistent result, which means that there is a trade-off effect between increasing sensitivity and decreasing specificity. For example, in dataset A and B, since the decrease in specificity is greater than the increase in sensitivity, so geometric accuracy tends to decrease as tau decreases. On the other hand, in dataset C, D, and E, the increase in sensitivity was greater than the decrease in specificity, so geometric mean accuracy continuously tends to increase. This table shows the result of the second research question. It is the comparison of OPT UMSVM with EMSVM and UMSVM. EMSVM's tau is set as 1 for all data samples, and in UMSVM, an appropriate tau is set for the data imbalance ratio as to Lee and Taylor. Tau of OPT-UMSVM is the a result of searching for tau by threshold moving masses. In this table, in all datasets, OPT-UMSVM shows best geometric mean accuracy. In particular, it is significantly different in highly imbalanced dataset D and E. This means that OPT-UMSVM is more robust than the other two methods. This is contributions and limitations of this study. This is the first study to optimize of UMSVM, and this is the first study to adopt UMSVM in finance domain. This study presents diverse measurement about UMSVM effect. As limitation, first, in extremely imbalanced data, UMSVM is not enough. Minority class needs more margin. I think UMSVM needs to be applied with cost-sensitive SVM because cost-sensitive SVM can enlarge total margin. Second, UMSVM is appropriate to only binary classification. To multi classification, I'm considering the distribution of overall margin. A recent study by Jong and Jong reported a new margin theory by increasing the average margin and lowering the variance simultaneously. By combining this technique with OPT-UMSVM, I'll do the future research.